All right, welcome back. Today, as I just mentioned, introducing it to you guys, we're going to answer the first part. It's a two-part answer to a one-part question. We know how to add vectors. We know how to subtract them. Can we multiply vectors? And the answer is a two-part yes, but there's two different ways to do it. And the first way that we can consider this idea of a product amongst vectors is something called the dot product. This is what, right now, the dot product, you're not going to use it for anything right away. You're like, oh yeah, that's what it is. Like when you add vectors, you get this other vector. That's not going to happen right now. What's going to happen is I'm going to show you the operation. We're going to treat it like an operation. I'm going to show you like 10 different ways we use it. So the dot product is in lots of stuff. It doesn't specifically give you anything right now that you're going to completely understand right away. Don't worry about that. I just want you to focus on operation, and then through the course of this lesson, I'm going to show you a lot of ways that it's used. You guys get the idea? So, first thing, what the dot product does. It is a way to multiply, but it does something kind of special. What it does, it takes the components of the vectors, our position vectors. It multiplies corresponding components and then adds that all up. So it adds the product of corresponding components. That's what a dot product does. So what this does, write this down, is a dot product is going to add the products of corresponding components of your vectors. There you go. Oh, right. What's that mean? Because if you've never seen it, like I don't even know what you're freaking talking about right now. Let me show you. It's actually really easy to do, but you got to do it at least a couple times to get the hang of it. So let's imagine that I've got a couple vectors. I've got A, and I'm going to use this vector bracket notation. And B. Leave this blank for a second. We're gonna discover what that actually does with our first example. It's gonna be interesting. It's gonna be like what, and we'll talk about that. So let's look at what this would do. So it says you're going to be adding some stuff together, but the stuff you're adding is a product of corresponding components. That means pieces that match up. So like the X components, multiply those. The Y components, multiply those. The Z components, multiply those. And then when you have multiplied those, add them all up. So what this would do with these two, it would do A1 times B1 plus A2, that's our Y components here, A2 times B2 plus A3 times B3. Do you guys see what I'm talking about, the products of corresponding components? You guys see that? Yeah. Say, take your X's, multiply them. Take your Y's, multiply them. Take your Z's, multiply them. These are in our vectors. And when you add them, what this gives you is A dot B. If you are talking about vectors and you put a little dot in there, that's one of our signs for multiplication, right? It's one of our answers here. That's called a dot product. So that the dot between vectors means a dot product. Head nod if you're okay with that so far. Now, this is what's a little weird about it. Check this out. Vector, right?
Yes.
Okay. Yeah. Vector?
Yes.
Vector?
No.
No. Component.
Yes. Yes.
Vector?
No.
Component. Vector?
No.
Vector?
Yes.
No.
Oh, wait.
No. Scalar. Weird. This dot product operation is a way that we multiply our vectors, and it actually gives us a scale. This is going to give you a number. Oh, that's all it can do. Look at that. You're multiplying numbers, you're multiplying numbers, you're multiplying numbers, and you're adding numbers. That's all you're doing. It's not a vector. This is equal to C, a scalar. So what I had you leave blank up here, this adds the products of corresponding components of two vectors, and it gives you a scalar. How we use that scalar? Oh my gosh, it's used it's used in a lot of stuff that we're going to be doing. Okay, we always use it. It's not hard, man. It's really easy. But you need to know that we're not getting a vector out of it. That's why it doesn't make a whole lot of sense right now when we say, hey, let's multiply them. What's it give you? It's a number. It's not a vector. It's a way that these vectors relate to one another. Yeah, and we're going to talk a lot about that. But for right now, the thing I want you most to understand is that we get a scalar out of this dot product operation. Show of hands if you do understand that. That's fantastic. Let's practice a couple, just one right now to make sure that we got this, and then we're going to continue. Actually, you know what? Do you think you can do it? Can you do it on your own right now? Can you find the dot product of V and W? Can you do that?
Yeah.
Let's try it. It's kind of one of the easier things that we get to do in this class. Oh man, we're multiplying stuff and adding it. That's awesome. As you're doing it, I want you to think about this. I want you to think if it would matter the order in which you did a dot product. Don't answer it now. Just do it. Do this. Figure out the dot product of V and W. Make sure you're getting a scalar out of it. And then we're going to talk about some of those properties. Can you reverse them? Can you distribute them? Can we do things like this? Have I given you enough time to at least do the dot product of that thing? Let's see how it works. Honestly, there's not a whole lot of work I need you to show here. Frankly, I don't care. Me personally, I show it because it's really easy for me to make mistakes in my head, like negative, positive sort of thing. So I at least show the three numbers before I start adding them together. Does that make sense? I'm going to show you everything for the first two, but after that, it's kind of up to you. So here's what the dot product does. It says, number one thing, you got to have two vectors for a dot product to make sense, and you got to be able to identify the x components and multiply them, the y components and multiply them, and the z components and multiply them. So let's look at the x's first. What are my two x components? One from each vector. What is it? Good. Does that negative matter?
Yes.
It doesn't matter when we're doing magnitude because we're squaring stuff, but we're not doing that now. So the negative matters. So this is x component, product of corresponding components. We got that. Then we're going to add some stuff. Now we look at the y component. Come on, everybody, kind of quickly. Y components, what are they? Y component, include the sign. Of course, we got -3. Y component, we got 2. And then we're going to add together the product of the z components. What's the z component here?
1.
Good, okay. And yeah, that's pretty much all that is all the dot product does. You go, okay, well, we got -2, we got -6, we got, how much is that going to give us?
10.
How much?
10.
Does a negative matter? Yeah, it does matter. It's not a magnitude here. It matters. So the dot product of V times W is -10. It's not a vector. It's a scalar. What's that scalar mean? I don't know. Right now, I don't know. Okay, it's just an operation. As we move forward, we're definitely going to know what this thing means. Okay, but right now, it's can you do the dot product? Show of hands if you can. Easy, medium, hard.
Easy.
It's really easy. I mean, you're multiplying numbers and adding them, and that's as hard as it gets, right? Because it's a 3D vector. We don't have 4D vectors, so that's fantastic. So literally, all you got to do is multiply three sets of numbers and add them up. That's it. You with me? Now the properties, as you're working through it, does it matter if I reverse these two numbers and reverse these two numbers and reverse these two numbers, which means that the dot product has commutativity. It doesn't matter. The way that you multiply those numbers is commutative, and since this is multiplication and addition, those are both commutative actions or operations, this is also commutative. And there's some other ones. If we have an addition of two vectors and we dot product that, it's also distributive. If we have a scalar, so scalar times a vector and then we dot product with another vector, it's associative, which means I can move that scalar wherever I want to because I'm just multiplying through anyway. I can do this, I could do this one. So I could do the dot product first and then multiply with the scalar, or I could do scalar times the second vector and dot product. What I'm saying is it doesn't really matter. Wherever that scalar's at, you're going to get the same answer. Real quick, if you're okay with those ones. They're kind of intuitive. It's like, oh yeah, this stuff, same sort of stuff we have with most of our math. This is a little weird. It's the first time I've introduced it here. That little zero with a vector on it means the zero vector. If you don't know what that is, it's kind of basic, but it's the vector that doesn't go anywhere. It doesn't point anywhere. It's still a position vector, but it's this position vector. It's 0, 0, 0. So it's at the origin. It literally is the origin considered as a vector. Guys, are you with me?
It's just a point there.
Yeah,
Considered a vector.
we can use it as a vector. Yeah, and otherwise, if we didn't have a vector, I couldn't talk about the dot product right now. Does that make sense? So the zero vector times any vector, it gives the zero vector back again. I mean, multiplying by zero, right? And that's basically what we're doing. So you go, hey, multiply everything by zero. You're going to get zero. You're going to get the zero vector.
But you won't get
I'm sorry. Yeah, I made a mistake. You're going to get zero. So when you add them together, you're going to get zero. Yeah, erase that vector because dot products always give us a scalar. Now the last one's, man, it's really interesting. What happens when you dot, we're going to spend some time on this, okay? What happens when you dot product a vector with itself? I want to go through the work and kind of prove this out because we get a couple results that are interesting that I get to use later. Are you guys ready for it? So what would a vector dot producted with itself look like? Let's consider this to be that V1, V2, V3, and then we're going to dot product that with another V1, V2, V3. It's going to be the same exact components. You follow? So that would look like this. Oops. Pretty straightforward. Hey, if I asked you to, could you do the dot product on these vectors right now if I asked you to? Okay, quickly, what's the first two things you're multiplying together? What is it? Just like we did. Plus what? I'm guessing you know the last one. True or false? That's going to give me a vector. True or false? What's it going to give me? Just like every other time a dot product works for us. It's going to give us a scalar. That's right. But wait a second. Wait, there's more. How else could you represent V1 times V1?
V1 squared.
Awesome. But there's more than that. In fact, this looks real. If I asked you to find the magnitude of V1, could you do it? Explain to me, come on, quickly, how you find the magnitude of V1. What do you do? Square root. Okay, you have a square root, right? And then inside the square root, what would be there? X component squared. Plus the y component squared. Plus the z component squared. Exactly this piece would be inside of the magnitude. Does that make sense? This right here is the square of the magnitude. That's exactly what it is. In fact, I'll prove to you. that undoes whatever I'm doing, right? So square root square, gone. It's all positive, so I don't have to worry about negatives because I'm taking these numbers and squaring them and adding them, it's positive. Now that one, I mean, you've got to be okay with it, but that is the magnitude of V1. Are you following what I'm talking about? That's it. This is the magnitude of V1 squared. So this is the magnitude of V1 squared. Which means we got a couple things I'm going to write up there. I'm going to kind of move up to the top of the board. A couple things I want you to know, some corollary, some really interesting stuff that we're going to use. Right now it's like, okay, that's awesome, man. What are we going to use it for? I'm going to show you as we're going through the section, okay? Right now we're just kind of building properties because it's probably the first time you've ever seen the dot product unless you've had this class before. Or like a physics class where maybe you had to do it. But you're like, what's it all mean? I don't know, you just do it. So we're figuring out what it means now, what we can do with it. Did you follow this? Hey, dot product, the same vector, you get the same components. Obviously, it's going to be squared. That looks great. But wait, that's the inside of a magnitude, which means it's the magnitude squared is what that is. And that's one of the three pieces we're going to write right now. So here's how we can think of a little subsection. So 5 continued, if you will. The first thing we can think of is if you want to dot product a vector with itself, it's pretty easy to do because of literally all you're doing. And you're like, well, this doesn't look easier. It's finding the magnitude and squaring it. But what that means is that all you have to do is take one, and it's common sense. I mean, it's common sense right here. You're just squaring the components. So if you ever wanted to dot product a vector with itself, you literally just have to do v1 squared, v2 squared, and v3 squared. But we use these facts in some proofs later on. We're gonna be using that stuff, so it's valid for us. It also means this. If you wanted to do magnitude another way, and you've already calculated the dot product, which I don't know why you would, but you can solve for that. So it's a different way to think about magnitude. So there's some kind of interesting little tools that we have up here. I want to know if these make sense to you. This one probably should be the most obvious one, okay? It's to say, yeah, same components, squaring. That's all you're doing. But I need you to understand that when you do that, what you're getting is the magnitude squared. You're eliminating the square root. You're squaring it. It's no square root. That's it. That's what I want you to get. Show of hands if you do, you feel okay with it. All right, let's move on. Let's go ahead. We're going to try three examples with the following vectors. This is purely for practice. I just need to make sure you're getting this down, okay? So I'm going to do maybe the first one for you, and the last one, I want you to do the middle one on your own. So that's what's going to happen. Do you feel pretty comfortable on finding the dot product when I ask you to? Yeah. Okay. You know, some people at this point get a little confused about the letter U. Am I talking about a unit vector right now when I put the U up there? How would I talk about a unit vector if I wanted to do that? It's a little hat. That's what would be there. So I'm using a lot of different letters so you get used to it. I don't want to just always use A, B, and C or V and W because a lot of textbooks out there use a lot of different letters. So I'm going to use a variety of them just to keep it fresh. But I don't want you getting confused like, oh, every time Leonard says U, it's a unit vector. That's not true. Every time I put that little hat up there, that's a unit vector. That's what that means. Like that. That's a unit vector in the x direction. All right, hey, practice time. Here's what we're going to do. The first thing I want you to do is, we'll do this first one together so you get the hang of it. If I asked you to calculate this, v dot product with w plus u, could we do it? Yeah, of course. Could it be possible? Well, maybe. That's what I want you to think about actually first. Is it possible first? And second, what are you going to end with? Are you going to end with a scalar? Are you going to end with a vector? Can you even do the work? So let's try it. What's going to happen when you add together w plus u? Are you going to end with a vector or a scalar?
Vector.
Very good. Can I dot product a vector with a vector?
Yes.
So that's possible. What am I going to end with?
Scalar.
Beautiful. That's exactly what I want you to think about. Because sometimes, the book's tricky. They put one up, oh, not possible. Oh, crap, I'm trying to dot product a scalar with a vector and you can't do it. That doesn't make sense. So let's go ahead and try this. I don't really care how much work you're showing or not showing. Show enough so that you don't make the silly mistakes. You know what I'm talking about. Sign errors, things like that. Me personally, I would do it this way. I'd write out this vector. I'm not trying to dot product that right now. I want to make sure I know how to add vectors, those two vectors first. So I'm hanging on to this one. I need to translate one of these. I don't care which one, but I'm going to always give this to you so you practice that translation. Since that's already in that vector format with those brackets, I'm going to be trying to do that. And then I'm going to be adding w and u together. So I'm looking x component, I'm looking x component, and I'm adding it. How much do I get with that?
0.
Do I need to write the 0 in this format? Do I need to write the 0 in this format?
Yes.
If I had i's and j's and k's, do I need to write it? Okay, cool. So I need to write the 0 here. How about, oh wow, how about the next one? What do I get?
0.
I'll give you a really funny example. How about the next one? What do you get?
2.
You're adding. That's one of the little mistakes, right? Be careful. Be careful on this stuff. Won't that suck when you get to your first Calculus 3 test and you know how to do all of this and you go, oh, I get 0 when I should have got 2. Are you going to be very happy when I hand that back to you? No. You're gonna be so mad at me. I'm like, hey, dude. Or if you're a girl, like, hey, chick. No, I'm going to say that. But no, you're not going to be happy. Be careful. Please be careful. Even if you have to bust out your calculator and do it problem by problem, I don't care. Make sure you get the right thing. Better get the right answer slow than the wrong answer fast, all right? Take your time. Not too much time, but take your time. Well, now it makes sense. I got a vector dotted with a vector. Let's go ahead and let's finish this off. Dot product does one thing and one thing only. It takes corresponding pieces, so it's nice to have the same format. It multiplies them, and it adds them. Did it give us what we expected? Did we get a scalar like we thought we would get?
Yes.
That's what I wanted. Think about what you're getting first, then make sure you're getting that thing. Can you try one on your own here real quick?
Yes.
Okay. The answer to that question, by the way, is always always yes. So. Here's my question. I want you to think about this before you answer it. Maybe just hold it inside for a little while. Here's what I'm going to ask you. Don't answer it now. Is that a dot product? Is that a dot product? And then what are you going to end with? Think about that before you start, and then do the problem. Okay. You don't need to answer out loud. Just keep it up here. If you finish that one really quickly, I'll put our last example over here, and you can try work on that on your own as well. I know you're still working on it, but I wanted you to think about this. Here's my question. First question, is that a dot product right there?
No.
Why not?
No good scalar.
What's that give you?
Scalar.
Scalar. It's just a scalar times a
Vector.
Is that relevant? Can you do a scalar times a vector?
Yes.
What are you going to get out of it?
Vector.
You need to be ending with a vector here. Does that make sense? You get it. That's fantastic. Now let's see what it is. First thing I'm doing is doing the dot product. The dot product here gives us, and you can do it like this if you'd like. You can do -2 plus -12 plus 2. If you want to write it like that, that's fine. That's exactly what we're going to get. Multiply this, -2. Multiply this, -12. Multiply this, 2. Just don't make a sign error. Do not do that. And then we go, okay, after we find that scalar, just that number, then we're going to be multiplying it by this vector. Not too bad, but you definitely have to understand all the operations involved. Show of hands if you made it as far, you feel okay with that one. How much does all of that work out to? -12, yeah, -2, gone. So we got that. Could you keep going? Could you stop there? Not really in this case. When you have unit vectors, yeah, you can stop at that. When I ask you to do a full operation, I want you to do it. So let's go ahead and let's continue here. We would distribute this scalar through our vector. 48 minus 12. And hopefully I got it right. Did you guys get the same thing I got?
Yeah.
Sounds good. Are you sure you're okay with it? Does it fall under like easy, medium, hard for you? What do you think?
Easy.
Not too bad. But you got to understand how to do it and don't make the sign errors. Oh my gosh. That's what causes your teacher to drink at night. Do you know that? Calc 3, oh my gosh, yes. And doing the integral of cosine and giving me negative freaking sine. Oh, if you do that, I swear, my wife is not going to let us be like, I hate lies. My students are killing me. You're literally killing me. Literally, it breaks my heart just a little bit every single time. It's like, no, the integral of cosine is positive sine, not negative sine. Plus C, freaking kids, you're killing me. You're not even kids, all right? But it kills me, so don't do that. And don't make sign errors. Now the last one. Did you start working on that as I was rambling off and lamenting about my poor, sad life when I go home? That's not sad. It's awesome. But anyway, I didn't tell you I won that $1.4 billion on the lottery? Now you're really thinking, aren't you? I didn't. I wouldn't be here. I tried to lie to myself, like, yeah, I'd still go. I was like, no, I wouldn't, dude. There's no way I could do that. I might. I don't know. Now I'm dreaming. Sorry, I didn't win the lottery. Let's continue math because I have to make a living somehow. So, did you start it? That's fine if you didn't. We'll do it right now. I wish you would have, though. Would have made me look good on camera. Thanks a lot, people. So, what are you going to get, though? What's this? Going to give you? Scalar vector. What's just this inside piece?
Vector.
Good darn thing, because you can't take a magnitude of a non-vector. All right, it doesn't make sense. That would be called absolute value. So we have vector. Magnitude gives us scalar squared plus the same exact thing, but you're adding. So another scalar. We're going to end with a scalar here. I'm going to go quite quickly through it, see if you can hang on. I want your participation, though. If we do v minus w, that's just these two. What's the resultant vector that I'm going to get? Can you tell me what that resultant vector is going to be? I heard the 3. What else? We're subtracting. So subtract component for component. That needs to be this vector right there. Does that make sense? Now let's see if you're paying attention a little bit earlier. I'm going to work this side down, then I'm going to work this side down. We're just going to put them together, okay? That's how I would do the problem. So let's go all the way down with this thing. If you were paying attention earlier and you kind of saw this, what's an easy way to do the magnitude of a vector squared? Tell me how you would do that. Square each of them. Would you take a square root? If I want this, it's the same as this. Just square them all. That's all this is going to be. Does that make sense? Otherwise, you can do the square root and then go, oh, and then I got to square it. That's a waste of time. So this says, hey, let's do 9 plus 49 plus 1. 3 squared, 9. 7 squared, 49. 1 squared, 1. Explain to me, in your own words, why I don't have a square root around it, even though it's a magnitude. Why don't I have that?
Because the square on the outside cancels that out.
Very good. Yeah, the square here says magnitude square root. Square, gone. It's this idea. How much? And then we're going to add something to it. Have you already added up the V plus the W? Have you done that? Right side, tell me what it is. What'd you get? Negative 1, 3. Are you finding what I'm talking about sign errors? Have you done some of those yet? I do them all the time. I try to be careful, but it happens. That's why you got to double check your work on these things, even though it's fairly easy, it's straightforward. I mean, you're doing like at most pre-algebra level stuff, but it's very easy to go, oh, I'm working with the wrong vector, or oh, I just subtracted, I should have added, something like that. Okay, it's really easy to do that. So I'm gonna double check right now. So let's make sure we're right. Negative 4 plus, is that right? Oh no, that's the wrong one. So 4 plus negative 3 plus, okay, I got that one. Looks like we're good. How do I get this again? 1. How much do I got? All there.
11.
Total of? That's what I want to see. Show hands feel okay with the idea. Any comments, questions, anything before we continue? Because it's going to get real after this. You're going to find the first thing out about dot product and why we use it. So anything, do you feel okay on doing dot product and understanding whether we're going to get vector or scalar when we're doing this stuff? Yes, no? Having fun yet? You can lie, just say, yeah. I'd rather be no other place. I don't want to win the lottery because I want to learn this. Right. You know you're a super math dork when you get excited that the whiteboard erases cleanly. That's when you know. I made it. I finally made it. Yay. Do you know what the law of cosine says? Random question. He's like, how does that relate to anything we're doing? Very strongly. Do you know what the law of cosines says?
Yeah. Well,
You do? I don't. I have to look it up on my notes here real quick, but I'm going to write it down. So, law of cosines. Law of cosine says if you have this triangle, any triangle, where the angles of this triangle are given by these capital letters A, B, and C, and the lengths of the side, keep this in mind, please keep this in mind, the lengths of the sides are given by little a, little b, and little c. So stand for the lengths of the sides. What the law of cosine says is a way to relate these angles to the lengths of the sides. It says this. Just so you know, those are 3 numbers in there. This is all right. Hey, take this triangle. What I know is that the length of A squared, little a, length of A squared equals this squared plus this squared minus 2 times this length times that length times the cosine of the angle between those lengths. Look at the relationships of what's going on, okay? Please understand something. This is the biggest thing I want you to know. This angle is between, same sides, right? Between those 2 sides. That's what I want you to know. Do you see what I want you to know? Yes, no. And it has to do with the length of the side opposite that angle. That's what I want you to do. Do you get what I'm saying here? Now, Why are we doing this? We just switched to trigonometry. We did, but maybe we think about it this way. I'm not going to use A, B's, and C's because we have a lot of those on the board right now. But what if we have two vectors? Oh, wait a minute. Dot product works with two vectors. That's interesting. And we're trying to talk about this angle. They obviously have an angle between them. And this is in 3 space, okay? So this doesn't have to be on a plane. This is just 2 random vectors. If they are not parallel, they are going to meet somewhere, and they are going, well, if we consider them to be position vectors, they are going to meet at the origin, and they are going to have an angle between those 2 things. You understand what I'm talking about? Well, let's do something. The first thing I want to do is build a triangle out of this. Oh man, are any of you guys good at all that stuff we practiced from 11.1? You know what that is?
Yeah, that's beta is equal to.
Nope, just this vector. What's that vector? Huh? Yeah, I know it's a resultant vector. I'm asking what vector it is. How would you relate it to V and W? Is it V plus W? No. If anything, this vector plus whatever vector equals this vector. That's how vector addition works. Well, you could do that. Call this, I don't know. Then W plus, I don't know, vector equals V. It's just symbols, man. It's just symbols. And if you solve for this, then I don't know vector equals V minus W. Solve for it. It's vector addition. All those properties actually do work. Then question mark vector is the resultant vector from that is V minus W. Quick show of hands if you feel okay with that idea. Did you know you could do that? It's pretty cool.
That's because they're like touching from head to tail, right? So
Initial, terminal, initial. V goes from initial to main terminal, and we can do vector addition, subtraction, just like that. Now here's what I'm going to do. What I'm going to try to do is fit this stuff on that picture. I've tried to draw it exactly the same for you, so let's first look at it. Can you tell me, and be careful with it, what's taking the place of A? What is it? Okay, hang on. One person said it, but a lot of you said V minus W, and that's not right. And I said for a reason. Think about it. I said this A is what? I said it.
yeah,
You should memorize every word that I've said. This is what's the A stand for? Come on, what's it stand for? Length. Is this a length? No. How do you find the length of a vector? Oh, crap. Okay, so when I'm talking about A and I put it on this picture right here, the thing that's corresponding with A is the magnitude of V minus W squared. Oh my gosh, we just talked about all that right now. What? What's it equal to? Let's fill it out. What's B? Okay, tell me what B is first. What's it represent? The little b. What's it represent? It represents a length. That's right. What vector is overlaid on top of B? Which one? So we're talking about this. How can I represent this idea of a length of a side, given that that's W? Come on, quickly. What is it? All I heard was W. But I'm imagining you said magnitude. The magnitude of V squared. Let's see if you can follow it. I want to make sure. We've talked about it just right now, but I want to make sure. Do you understand that A squared, the length of this, is the magnitude of V minus W squared? Head nod if you do. I need to get through it. Do you understand that the W part. The B is the W part. It's the magnet. This is the length. It's the length of W squared, the length of V squared minus, this is the weird part, it's 2 times the length of W times the length of V times the cosine. This is how I want you to think about it. Not cosine of theta, whatever theta is. It's cosine of this. Please listen. Times cosine of the angle between whatever those two vectors are. This A is the angle between these two sides. This theta is the angle between these two vectors. Do you guys get what I'm talking about? That's important. So theta, yeah, I know it's the only angle that I've listed, but it's the angle because it's between these two sides. It has V and W adjacent vectors. You get what I'm talking about? We're going to do a whole lot of work. So first thing, keep this all in your head. We're going to work just on this side. We're going to do a lot of the stuff that we just talked about. Number one, the reason why we actually did this was for this. I now have a magnitude squared. And what I know from this, and this is the big deal, okay? Here's like the punchline of this. Are you ready? You're not going to be ready. These are like, shut what? This is where the dot product comes in, okay? Right here. Do you see how I have a magnitude squared? A magnitude squared is a dot product. It is. So this side, what this gives us is V minus W dotted with V minus W equal to the same bunch of crap that I'm just going to have up there because I'm lazy and I don't want to write the whole thing. Make sense? Have I lost you yet? You guys kind of have fish eyes out there. Are you guys okay? This is the fun part. Come on, we actually get to do something. Don't give up on the easy stuff. I'm like, oh, I just want to add stuff. Come on, I can do dorky voice to you too. Can we do that? Let's do dorky voice. Teach the whole class just like this. All my subscribers gone. Sorry, guys. I want to do dorky voice, but you got to get what I'm talking about. A magnitude squared is a dot product of this inside thing dotted with the inside thing. Do you guys get it? But wait, we just learned that dot product is commutative and it's associative. It's all these things that we normally have, which means that we can do this. Equals same bunch of junk. Guys, are you okay with that? I'm literally just distributing. Can you guys do that? Okay, here's the awesome part about it. You know how we did this, right? We said, hey, magnitude squared is a dot product of the same vector dotted with itself, correct? We can go backwards. If this is V dot V, V dot V is the magnitude of V squared. Are you paying attention? We're proving something pretty substantial here that we're going to use for a lot of this, at least this chapter. This I want you to hang on to. Keep it right there. This same thing, magnitude of W squared. Did you write it down? I don't want to lose you. You got it? Equals all of this stuff and then the magic happens. Yeah, I'm going to write it in purple so you guys see the transition here. So the stuff in purple was the stuff we originally had right here. Now I want you to take a close look at it. Can you see some pretty cool stuff that's going to happen? Cancellations. That means when we subtract. Hey, can we subtract? Well, let's think about it. Vector or scalar? Come on, everybody, quickly. Vector, scalar. You can subtract scalar. You're subtracting numbers. That's it. That's all it is. It's a number. Gone. Gone. Cool. Anything else? I see more. Go on. Go on. Yes, no? Now, we're all adult mathematicians, right? So we can do a couple things at once in our heads. We've just eliminated this and this and this and this. We have one term equals one term. They both have negative 2's on them. I know I'm not going to add negative 2, but I could divide by negative 2. Do you see it? So when I do this, do you need to see that step? Do you want me to write that for you? Yeah, okay. I'm also going to switch these around. They are scalars. That means they are numbers, which means we have commutativity, which means I can just switch them. Why? Because I wanted to match up and look nice. Now you see it. Go, okay, hey, let's divide by negative 2. Then this is gone. And here's what we end up with. Number 1, we end up with this, which is pretty cool. Check this out. You don't even think it's cool yet. You will. You end up with a different way to do dot product. So, hey, if you want to do the dot product, yeah, it's pretty easy to do. But let's say you didn't even have the vectors themselves. Let's say you just had the lengths of the vectors and you had the angle between them. Could you do the dot product with the lengths of the vectors and the angle between them? Yeah. Length times the cosine of the angle between them. That's a different way to do the dot product. That's pretty cool. Here's the other one, the main core. So that's number 1, okay? And I'll list that out in a little bit also. Here's the main one. Can you solve for cosine theta? That's one of the big reasons we need the dot product. Why? What's it do? Nothing, I don't know. Don't pee your pants, it's okay, it's fine. That's what it does. It gives you the angle between any two vectors that you want. So let's say I give you V and W, or A and B, or any two vectors in the world. Could you find the angle between those two vectors? Absolutely. That's pretty easy. You know how to find, what's that mean? Scalar, right? Magnitude. This one's a magnitude. Do you know how to find magnitudes? You better at this point. Do you know how to find a dot product?
Yes.
Scalar, 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 scalar. Can you figure out an angle if you have cosine theta equal to a number? Yeah. All you got to do is, hey, cosine inverse of whatever this is. Done. You just found the angle between two vectors. This is how you find the angle between any two vectors. It's pretty cool. And the reason why I wanted you to notice what the theta was is because theta is the one that we defined to be between V and W. So when we did all this work, that's the angle we're finding. No other stuff. It's the angle between any two vectors that you dot product and divide by the magnitudes. Which is neat. It's pretty cool. Couple notes, actually a lot of notes that I want to do here. The first note, you need to make a note that this works for theta between 0 and pi. So it's not 0 and 2 pi. And here's the reason why. If you have an angle, think about this for a second. If you have two vectors, right, and your angle is, this is my 5th favorite dance move behind the 1 over x, you know that one, it's favorite, but it's this one, your angle moves, okay? So if you have this angle that's more than pi, you'd be able to go this way and get a smaller angle. Does that make sense? So we max it out at pi because anything further than that, it's a smaller angle the different way, which is what it's going to give you. So that's number one. Now how about this? What if theta is 0? Or if theta is pi? Just think about it logically for me, okay? Think about if you have two vectors and the angle is 0 between them. Tell me something about those vectors. Oh, wait, same vector? What if they're different lengths? Are they the same vector? No. Same. I love how one of you said same unit vector. What's the same unit vector mean? Yeah, you're right. Same direction. What happens if two vectors are going the same direction? What are they? They're parallel. So if our angle is 0, we have parallel vectors. What if our angle is pi? Do we also have parallel vectors? Yes. Opposite direction, but they are parallel. Does that make sense? So if this happens, if theta is 0, if theta is pi, we have parallel vectors. What about this one? And we're going to work with this one. This is going to be kind of cool. Come on, think about what we just did, okay? What if the angle between two vectors is exactly pi over 2? Come on, what is it? If the angle's 0, they're going the same direction. If the angle's pi, they're going opposite directions, but we talked about having the same unit vector, right? Which means parallel. They're scalar multiples of each other, just a negative. That means parallel. Vectors that are scalar multiples are parallel. That's important. What if the angle is pi over 2? What do you know about those vectors? Perpendicular. We have a different word in Calc 3. We throw a lot of words around that mean the same thing. One of them is perpendicular. One of them, this means the same thing, is called orthogonal. Can you say orthogonal? Orthogonal, yeah, it's a weird word. And the other one's called normal. Normal means perpendicular also. Orthogonal and normal, when we use those, it has a connotation that we're in 3 space, not just like perpendicular on a plane, okay? So that's why we use them, but it's no different. So if we have theta equals pi over 2, we got perpendicular vectors. We call those things orthogonal or normal. We also talked about this. I'll move over here a little bit. Before I do that, I want to do like a 30-second recap just to make sure that, man, we just did a ton of stuff, all right? And we proved it, which is pretty cool. I probably could have just given this to you, but you'd be like, what? Did you follow that proof? Oh, crap, don't make me redo it. Oh, my goodness. Did you follow it? Please, I'm begging you here. Do you know how to find the dot product between two vectors?
Yes.
Do you know how to find the magnitude of any vector I tell you? Pretty easy stuff. Now, using this, that we just proved it, we now know how to find the angle. It's based on the law of cosines. We just took some lengths of vectors, those are called magnitudes, we put them in the law of cosines, we solved for the cosine of the angle between two vectors. That's what we did. If you can find the dot product of magnitudes, you can always find the angle between two vectors using just a cosine inverse. Have I explained that well enough for you guys to understand that? Okay, after that, we go, okay, well, what happens? Well, what are the corollaries here? I mean, what's the purposes? Well, we know a couple other things. If the angle between two vectors is 0, they're in the same direction. They have the same unit vector. If it's pi, they're a scalar multiple, just a negative of each other, maybe more or less. But that also means that they're parallel. If we have pi over 2, we have this 90-degree thing. That means orthogonal, these perpendicular vectors. And now I'm going to use this, the alternate form of the dot product, to show you something that's pretty neat. Well, you'll see. So let's use the alternate form of the. Are you focused in right now? Have I just kind of beat your heads into submission just a little bit, or are you going?
All I heard was normal and abnormal.
You didn't even hear abnormal because I never said it, but that's okay. don't think I did. I'll have to watch that video. I don't think I said abnormal. That's something in psychology. I'd already told you they won't give me a psych degree. It'd be too dangerous. Yeah. I wish. It'd be awesome. I wish I was a psych. No, I don't. I got too many problems to deal with other people's. So, you believe that, right? Because it was like halfway through our proof. I proved it. It was there. Now, let's take this and run with it. If two vectors are perpendicular, orthogonal, normal, the angle between them will be pi over 2. Are you with me?
Yes.
So, for perpendicular vectors, for orthogonal vectors, theta equals pi over 2. Nod your head that you heard me, you understand the concept. Let's plug it in. Let's see what. Let's assume that V and W are perpendicular or orthogonal. Okay. So if V and W are orthogonal, then the angle between them is pi over 2. Nod your head that you're with me. Let's do it. So then V dot W would equal, okay, whatever this is, times whatever the magnitude of W is, times cosine. But wait. If you're assuming that V and W are perpendicular, and we know that the angle between them is pi over 2, by the way, verify this. You can't have 3 pi over 2.
You can't. No.
Can't. Because if you went past pi, you could have measured it the other way.
Okay.
Make sense? We don't care about 3 pi over 2. We care about pi over 2. Pi over 2 is perpendicular. It's orthogonal. You follow? Now you tell me right now. What's cosine of pi over 2?
0.
What's a scalar times a scalar times a 0?
0.
I'm getting the chills right now. It's so cool. This is how you show that two vectors are perpendicular. If you do a dot product and you get 0, the only way that happens, look, the only way, that's a magnitude, right? If you have a non-zero vector, so it actually has a length, that cannot be 0 unless you have the 0 vector. If you have a magnitude, it's non-zero length. It's not the 0 vector. So given two actual vectors, the only way this ever happens is if you have pi over 2. Everything else cosine has a value for. Does that make sense? And you can't have 3 pi over 2 because get that little. So this right here, so if I ask you on a test, how do you show that these two vectors are perpendicular? How are you going to do it? Dot product. If the dot product is 0, are your vectors perpendicular?
Yes.
If the dot product is not 0, are your vectors perpendicular?
No.
That's it. This is how you show two vectors are, I'm going to use the fancy word, all right, orthogonal. Or perpendicular, it's the same thing. Hey, not if you're still okay what we're talking about. A couple other things. I want you to think about this for a second. You know what I, J, and K are, correct?
Yes.
Tell me the relationship between I and J and I and K. I and J are perpendicular. How about I and K? You can just, okay, nothing? I'm not getting nothing out of you guys. I don't know. I and J. Where's the X go? Sorry, I haven't wrote it. What's the I go along? What's the J going along? Tell me something about Y and X. Tell me something about Y and X and Z. All orthogonal, all perpendicular. Tell me something about I and J and K. They're all mutually, they're mutually orthogonal. I and J and K are mutually orthogonal, which means this. If you ever dot product I with J, what number are you going to get?
0.
Have to. If you ever dot product j with k or I with k, they're mutually orthogonal. You have to get 0 if you dot product those things. You can think about it, all right? If you dot product, I'll just do one example. 0, 1, 0, which is j, with 0, 0, 1, which is k, 0, 0, 0, 0. See? Every time. So these things, we would call them mutually orthogonal. And it says this whole stuff kind of comes down to, if you ever dot product I with j or I with k or j with k, and I'm not doing the reverse because we have commutativity, what are you going to get again? If you ever dot product vectors that are perpendicular, you have to get 0. In fact, that's how we prove that vectors are perpendicular. How about this one for those of you guys who are thinking outside? This can take a little bit more thought. A lot of this class, I want you thinking. I don't want to just give you this stuff. That's worthless. I want it to stick. And the way that stuff sticks is I force you to do it yourself and force you to think about it. I want you to think about, for the next minute as I'm writing some stuff down, what that's going to be. Think about what would have to happen to dot product this thing. And you can even write them out if you want to. I dot I. Write out what the vectors are and try it. See what it is. Write out j dot j. Write out k dot k. See what it is. And then think about why. Why that is. Don't just sit here blankly for the next minute and a half, okay? I want you to think about it. Okay, tell you what, we're about to take our break. We're going to talk about this. It's a single number answer, and then during your break, I want you to see if you can work on that. When we come back, we're going to go through it very fast because it's so basic. You said you know dot product. You said you know magnitude. So we're going to crush the problem, find the angle between them. It's very, very straightforward. But this is not so much unless you really think about it. Tell me something about I and I. They're parallel, and J. They're actually the same vector. They have to be parallel. And K. So if I dot product them all, I'm going to get the same thing. But what's the thing? 1. Why? Why in the world, when we dot product I with I or J with J and K, if you did it, you find it out. Do 1, 0, 0, dot 1, 0, 0. You're going to get 1. Same thing with J's, same thing with K's. You're going to get 1. Question is why? Well, just think back about it, and then we're going to take our pause, okay? In order for two vectors to be parallel, the angle between them has to be settled, correct? Tell me the magnitude of I right now. What's the magnitude of I?
1.
What's the magnitude of J? What's the magnitude of K? So if the angle between them is 0, what's cosine of 0? What's cosine of pi? Negative 1. But instead of the multiple, it's really just 1. Does that make sense? It's kind of cool. That's why we get this 1, because cosine, the largest cosine we get is 1 when we have an angle of 0 or an angle of pi, negative 1. But that means that we have this parallel idea. Have I explained things well enough for you guys to be able to do the cosine between angles? I want you to practice that, and we'll come back in 10. All right, welcome back. So let's get this thing done. Listen, it's not the hardest thing in the world to do, but you absolutely have to do it. Did you attempt to find the angle between these two vectors? This formula is pretty nice. It lets you do everything basically at once. So when I'm doing this, when I find the angle between two vectors, first I understand that the angle between two vectors, no matter how I look at that, dot product is commutative. Magnitudes are just numbers, and multiplication is commutative, so it doesn't really matter the order in which I talk about this. It's the same exact angle. So when we find the cosine of the angle between them, I start off like this. You can also start off with theta equals cosine inverse. That's fine. I don't really care. I always start with this and then do the inverse later. But here's how we do it. The formula that we had said you're going to find the dot product of these two vectors. Be careful on these vectors. Don't make sign errors. Obviously, sign errors are going to affect the angle, all right? So when we do this, this says that, and I'm going to write it out because I don't want to make a mistake. The dot product of V and W, since you guys are now pros at it, 0, because there's no i's. 0 times 1 plus negative 2 times 1 plus 3 times 2. Head nod if you're with me on that one.
Yes.
All this is that. Or W dot V. It does not matter. It's computed. Still okay so far? Now on the denominator. The denominator says, okay, we also need the magnitude of V, and we need the magnitude of W, and we're going to multiply those things. Listen, you don't have to write out all of the steps. That's fine. Just don't make the little errors that drive me nuts, and you nuts. But definitely make sure you have a square root on that thing. This is not a magnitude squared, okay? Unless you have the same vector, which you wouldn't, because you just get a 1 anyway, because you don't, well, you get a magnitude anyway. So here we go. Okay, 0 squared is 0. 2 squared is 4. 3 squared is 9. So I know that it's going to be 0 plus 4 plus 9. Do you see where that's coming from? We've done magnitude enough where you should kind of be familiar with it. We go, okay, hey, magnitude of V. 0, 4, and 9, because we're squaring those components, adding them, and then putting them under square root. Head nod if you're okay with that one. Times dot product or times? It's only a dot product if it's between two vectors. If not, you're just multiplying. Yeah, it's the same little dot. You should know what the vectors are and scalars are at this point. It's okay. The dot there means that we have just multiplication. And then the other vector. 1 squared is 1, 1 squared is 1, 2 squared is 4. We got it under a square root. Show of hands if you're really okay with that one. What's this again? Oh yeah, it is a scalar, but what's it coming from? So if we do all of this, that's 0, that's negative 2, that's 6. How much do we get on the numerator? Denominator, we have the square root of, looks like 13. Square root of, yeah. You can do a whole bunch of stuff with this, okay? You can multiply this and then rationalize it if you want to. If you want to do, I'm going to give you all the options that are acceptable, okay? So here's option number 1. Firstly, find theta. You don't leave it cosine theta, you find theta. How do you do that whole thing? What do you do? So if you do cosine inverse, these two things, if I've done it right, is 78, square root of 78. That right there is an exact answer for the angle. So what's the angle between them? Cosine inverse of 4 over square root of 78. Because it's not on a unit circle, right? But that's an exact answer. You could do that. You could rationalize and simplify. If you simplify that one, you get that. That's nasty. A lot of textbooks like to do that because they always like to rationalize. Me personally, I do not care. So if you give me this, that's fine. That's an exact answer. Give me this, that's fine too. That's the same answer. Can you approximate it?
Yes.
Can you approximate it in degrees?
Yes.
Just make sure your calculator is set to degrees, and then if you do that, just cosine inverse cosine inverse of whatever, probably this one's easier to put in your calculator. I think you get around 63.1 degrees. So make sure you can do that at home, get 63.1. That's the idea. I really need to know if this is enough for you guys to follow through and understand how to find the difference between any two vectors. Perfect. Let's try one more. I want to make sure you're not doing a slip up that a lot of people do, Daniel, when they're going through this, and I ask you to find parallel or perpendicular, okay? There's only one way to do this orthogonal perpendicular thing, but there's several ways to do that. I don't want you working too hard. I'm going to show you the easiest way, the go-to way. Are you with me on this one? So, number one thing, if ever you're asked to find parallel vectors, please only do this one way. The only way vectors are parallel is if they are scalar multiples. That's the only way that I want you to use. There's other ways to do it. You can use the dot product. You can use the cross product, which we don't know about yet. We could try to make them on a plane and do... Don't do that. Scalar multiples, so fast, just do that one, okay? So when we're checking whether these two things are parallel, it should be pretty obvious. It really should be pretty obvious. So for instance, can you make one of these into one of these by factoring out a number? If you can, they're parallel. If you can't, they're not. That's what the scalar multiple idea is, okay? So I'll start with A. And you go, well, wait a minute. Can I make that into that? Or could I start with B and get it? That's probably even easier. But could I make it into that? Yeah. Look at it. It has pretty much the same thing going on. There's a 2, there's a 1, there's a, this has a 3, that doesn't. Let's force this to divide out the 3. If I force this to factor out the 3, then this becomes 2/3. This becomes 1/3. And this becomes 1K. Did you catch what I'm talking about? It's probably easier to start with this one and factor out the 1/3, but it's the same idea. If you can factor out a number from one vector and get a number, scalar, times a different vector, that is how I want you to prove for all time that two vectors are parallel. This right here proves it. This says that A is a scalar times B, and therefore A is parallel to B. And that's the shorthand way that we write that. I really want to make sure I've explained that well enough for you. Are you guys okay with that one? Show of hands if you are, for real. Do you see what I'm talking about? Might be easier to start here. I just didn't. If you start here, factor out the 1/3. Might be a little bit easier to do, but it doesn't really matter. Find a number you can divide out, get the other vector times that number, and it's parallel. You with me? Now, how about this one? In actuality, do we have to even talk about that? If two vectors are parallel, can they possibly be orthogonal? It's kind of like different ideas, right? Well, let's prove that they're not. How do you prove they're not? Easy. Any two vectors that are orthogonal, when you dot product them, 0. Your result has to be 0. So therefore, if I take the dot product of these two vectors and it's not 0, they're not orthogonal. Are you with me? I wrote it down. I said, hey, the dot product is how you tell whether two vectors are orthogonal. If it's 0, they are. If it's not, they're not. Just go ahead and do that right now. I want to see the dot product of A dot B. That's how we say that, A dot B, and then I want to see what that result is. Okay, so go ahead and practice right now. We already know they're not because we proved they are parallel. Did you get 4/3 plus 1/3 plus 3? I don't even care what that is. What's it not? Therefore, A is not perpendicular to B. That's what I want you to show that as. If you understand how to check for parallel and how to check for perpendicular, would you raise your hand right now? In 2 words, tell me how you check whether 2 vectors are parallel. Scalar multiples, that's parallel. In 2 words, tell me how you check whether 2 vectors are orthogonal. Perfect, that's exactly what I want you to know. We're going to do this one light speed, okay? Really, really fast. Firstly, look at these 2 vectors. Just tell me in like a second if they're parallel. Are they parallel? With 0 work, are they parallel? Why not? It says to get from here, you multiply by 1, and to get from here to here, you don't multiply by 1. And you go, oh, no, it doesn't work. They cannot possibly be parallel because they are not scalar multiples. You guys get the idea? It's that easy. Don't do any other work for parallel vectors. That's it. That's it, for real. Scalar multiple. Are they perpendicular? Are they orthogonal? Well, that takes more work, right? You actually have to do something. There's no easy check there, unless you want to find the angle between them and then make sure the angle is 90 degrees. But that sucks, because we made a shortcut for that. Do the shortcut. Find out whether or not these are orthogonal. What's the shortcut? We just asked for it a little while ago. How do you check whether 2 vectors are orthogonal? Do the dot product. If it's 0, they are. If it's not 0, they're not. Were you all okay that they're for sure not parallel because they're not scalar multiples? It's pretty fast. I mean, it should jump out at you whether they are or not. Are you getting pretty good at the dot product? It's going to get faster. Huh? Orthogonal, yes, no? Done. Yeah, absolutely. These 2 vectors are orthogonal because their dot product equals 0, and we just proved that the only way that happens is if the cosine of the angle between them is pi over 2. That's the only time we get 0, and that proves that we have orthogonal vectors here. Do you know that I have a dog? I hate that dog. He's a great dog, but oh my gosh. Every time, we don't go on walks. We go on drags. Because it's me dragging him everywhere. Because he likes to sniff and poop. I don't know what's wrong with this dog, but he poops like 13 times a day. It sucks. I've worn out like 4 shovels, all right? That's saying something. So here's my problem, all right? We don't have a lot of hills, but there's a canal by our house, which is a security risk, and I don't really like that because people are right behind our house on the canal. So don't do that. So let's have a shotgun. Ha ha ha. What now? No, just kidding. I wouldn't ever do that. I do have a daughter, though. We're getting way off topic here. So imagine that I get a drag. I'm going to pull it's a drag, it's not a walk. I'm going to drag my dog up the hill for the canal, okay? I'm taller than my dog. So even though I have to drag him up this hill, so here's dog, I'm pulling like this. Is all of my energy going towards dragging my dog up this hill? No, I'm also doing this to him. So I'm also lifting him up this way, depending on how I am pulling him. And this is the depending on how. So there's an angle between where I want to pull him and where I'm actually pulling him. Here's what we are going to do right now. This is very physicsy. It's how much am I actually pulling him up the hill where I want to pull him? How much of my energy is going into that? What vector would this vector create if it was going in well, not if it was going this direction, but how much vector is there in this direction that that vector creates. The idea of the vector that V creates in the W direction is called vector projection. I love how that rhymes, by the way. The vector that V creates in the W direction is vector projection. It's just the directionality of that vector. It's nothing more than this idea. It's nothing more than this. Here's a vector. You don't need to write it, just watch. Here's a vector. True or false? I can always break a vector into its horizontal and vertical components.
True.
Think of this as the horizontal. Think of that as the vertical. It's the same thing. It's just it's not horizontal. It's along a different vector. Does that make sense? If the vector was not the x-axis, in other words, we're going to do that. So that idea. The idea of saying, hey, what's that component of, well, what's the vector that that V makes along W? What's that vector? That's a vector projection. How it's denoted is that please get this right. I cannot iterate enough to you how many mistakes happen on this problem. It's very easy. It's not even hard. It's just a little formula. But a lot of people screw it up because they have a misconception about what vector's projecting onto the other one. The vector projection of V onto W is written this way. Projection, so it's a vector projection. The vector you are projecting is written here. The vector you are projecting onto is written as a subscript. That's what's going on. That's the vector projection. So what this literally is, I'm going to show you, like, just with a picture right now. You ready? If I drop a perpendicular so I want the vector is saying that's the vector I'm talking about. It's not going to be the whole length of W. It's not going to be all the way from P to Q according to this vector. It's just going in that direction. That's the projection of V onto W. Show of hands if you feel okay with that one. It's a vector. Now, every vector has a magnitude. The magnitude is what we call scalar projection. Why? Magnitude scalar. We call scalar projection or component projection. Just the part of it that's going in the W direction. So every vector's got a magnitude. The magnitude of this one's called component projection. Basically, it says, hey, how much of this vector is moving along W? What's the length it would create there? And it's written like this. Component vector V onto vector W. This vector right there. we're going to work with it because it's got a lot of useful things, but we're going to build it a little bit. What we're going to do right now is we're going to build this from the component aspect of it, component projection, and then we're going to get the actual vector projection from it. And then we're going to do just a little bit of work with it, not a whole lot. You guys ready?
Yeah.
You sure? Do you understand the idea of vector projection? Yes or no?
Yeah.
Let's wait for the proof, and as we're going through the proof, it's going to make more sense. But then, if there's still like, I don't get it, then ask me some questions. I can probably answer them. Don't sit through here going, man, I have no idea what this guy is talking about, because that's not great. Okay, if you're already there and like, man, this is the third day, I don't know what you're talking about. That's the problem. All right, you come and see me, and we'll get you some help. But let's see if it makes sense after this. Same exact picture. We're still wanting to go my dog from P to Q, okay? Here's the way I want you to think of component or scalar projection for the first way. How much of V is being applied in the W direction? That's a magnitude idea. Hey, how much of my force I'm pulling on that dog's collar is actually moving the dog up the hill? Does that make sense? There's some wasted, some's being pulled this way. But how much of it is actually pulling him up the hill? That is the idea of component projection. So the amount, the magnitude of my V along the W direction, this guy is what we are talking about when we do this. We just got to figure out some ways to put it down mathematically. Now, there's something really nice about this. You see an angle up there, right? An angle between two vectors, and you also see a right triangle. Well, we know some stuff about right triangles, I hope, in this class. In fact, we know that if I did a relationship between this and this, what trigonometric function would relate this, which is this length right here of the right triangle? Do you understand that? The length of that is how much of the magnitude of V is going along the W direction. That's that little length right there. And we already have it. It's a component. It's a scalar. It's a component. It's literally a number. What relates this to that? Cosine. Cosine relates adjacent to hypotenuse. That's the adjacent. What's the hypotenuse? Be careful before you answer. What's the hypotenuse? Say it louder. The magnitude of V. Because cosine, but side relationships don't work with vectors, okay? They work with numbers. They work with scalars. Verify that's a scalar. That's just the magnitude that's being pulled along W, okay? This is not a scalar, but if I took the magnitude, it would give me the length of that, just like a right triangle wants us to have. Did you know that we're almost done? Like, we're really close. Can you solve for the component projection right now? How do you solve for it? Both of them. That's it. How do you find, you know what, honestly, it's a really trivial proof that I've just done. I mean, if you really think about it, this is any right triangle in the world. It says, hey, how do you find this length given this length in an angle? Cosine. Cosine. That's it. It's just cosine because that's how right triangles work. You go, hypotenuse times cosine theta gives me the adjacent side. That's literally all we're doing. Show hands, feel okay with that one. That's it. That's it. Now, this also says something, though. It says, in order to find this, you have to know the angle between the vectors. What if you don't? Well, so this is number one, okay? This is, yeah, I'll write it. Yeah, I'll write it later too. But this is going to be if you know the angle between these two vectors. If you don't, well, but we know this. This is pretty cool. We know how to find the angle between these two vectors. In fact, we know that cosine theta is v dot w over the magnitudes of those vectors. So if we continue, we got this. Let's just substitute it. Let's put this thing here. It's just algebra, but the just algebra can just kill you, all right? So I want to make sure that you're actually with me. Just a 20-second recap. Let me go through, make sure you got it. You understand the idea, firstly, that V is pulling something along W. The amount of that is called the scalar projection or component projection. And it's literally just, hey, cosine theta times this thing, because that's how right triangles work. And that's our definition of component projection. So are you guys okay up to this far? Head nod if you are. Yes? Yeah. What about this? You guys understand that cosine theta, we just proved it, spent like 30 minutes proving this. Are you guys okay with that one? If I take this and put it here, this V is this magnitude. All this junk is all this junk. Do you see anything that simplifies? That means that we have two formulas for component projection. The first one I've given to you. So the first way we find it that way. That's the first way. Or that. Why do we have two ways? Can you explain to me in your own words why we have two ways?
We have an angle in one.
Say what now?
We have an angle in one.
That's right. Hey, if you know the angle between your vectors and you want to do component projection, which one of these formulas are you using, the left one or the right one? For sure, he's got an angle. It's very easy, man. It's literally just cosine angle times magnitude done. You guys with me on what I'm talking about? What if you don't have an angle? Which one are you using? This one has the angle built in there. That's why we did it this way. So this is for, like, you know the angle, you don't know the angle. So you know theta, use that one. You don't know theta, use that one. I really want to know if I've explained this well enough, because we got to continue here pretty quick. We got to wrap this stuff up. You guys okay with it? Yeah. You sure?
Yeah. Around the.
How about this one? What if the angle between those two vectors is more than pi over 2? What's cosine do when the angle of theta is more than pi over 2? What's it do? That's right. Remember, all students. So for you guys, all students take calculus, right? So all would be cosine's positive, but then student, second quadrant between pi over 2 and pi, cosine's negative. Does that make sense? Think about the picture. If I am pulling past this, past pi over 2, what am I doing to that dog? I'm pulling it backwards. I'm pulling it back down that hill, so I'm pulling it negative. The magnitude becomes negative. Does that make sense to you? Okay. Now, here's what we know. So we're going to continue. We're going to do some, we're going to change this one. We're going to get to actual vector projection. And you'll at least have the formulas before you leave today. Before our extra, I guess. You know, in the most basic sense, vectors are really just a magnitude times a direction. here's what we know. So this is a little proof about getting to vector projection. So if I'm looking for the actual vector projection, every vector, man, I hope you can put it together, okay? Every vector equals a magnitude times a direction. Those words, man, they got to be up there. We just did it. What's the magnitude of vector projection? There's definitions like right up here, just erase it. Remember talking about how component projection is the magnitude of vector projection. If the vector projection is a magnitude times a direction, that is the magnitude. Now here's the question. Oh my gosh, if you get it, I'm going to go home so happy today. Otherwise, I'm going to go home and cry myself to sleep like I do most nights. Give me the direction. Please, just give me the direction. Just give me the direction. What's the direction? Okay, in this class, you know some word association because I'm trying to brainwash you here. Direction means
Unit vector.
Unit vector, very good. Unit vector of what? Unit vector of V?
No.
That's not where I'm pulling it. Unit vector of, yes. That's the direction. So vector projection says, hey, find component projection because it's really easy. And then go, well, what direction is it in? Whatever vector you're pulling it along, man. We're going along W right now. The unit vector of W. Don't do the vector W because that gives it more magnitude than you actually have. Okay, you'd ruin it. Unit vector of W. The direction of W. What vector you're pulling it along. You're projecting onto, I should say. Whatever this one is. Unit vector of W. Here's what we're going to do. We're simply going to take this piece. I'm sorry, lost. We're going to take this piece. We're going to put it right there. And we're going to do one thing with it. The only thing we're going to do with it is this here real quick. Check it out. You see a magnitude times a magnitude, right? That gives you that magnitude squared idea, which is really nice. That's the best format to work with this in. So that's the formula I'm going to give you. Do this first. Dot product with W, and that will give you the vector that this creates in this direction. That's what that does. We're going to work with some examples, but can you do it? Can you do it on your own right now? So the examples are going to be a little bit extra, okay? Could you find the dot product? Can you find a magnitude squared? Can you then scalar times a vector, and then you're good. That's the idea. All right, so now's our time for practice. What we're going to do is I'm going to show you how to actually do this. I do want it to make sense. Otherwise, I would have just given you the formula and said, "Hey, do it." But that sucks. So I want you to really understand it. So we're going to do this. I'm going to show you what this means. The biggest mix-up ever, like with doing these problems. I'm going to show you how it relates to work. It's like a physics aspect. I'm going to show you kind of a tricky problem dealing with just a dot product idea and an angle, and then we're going to talk about the whole unit circle idea, but in 3D, which is like maybe a unit sphere sort of idea that we're going to create. So the first thing, if you get what this is doing, it says, hey, what vector does V create along the W direction? Well, the length of that times the direction of W. That's what it's doing. It says, hey, you got this vector, it's going in this direction now. The magnitude is just the component projection, it's a triangle, times the vector that you're projecting upon. The direction of that vector. It's a unit vector. It's just saying, hey, that's the direction of W. Yeah, I know, it's a unit vector. That's how far I want to pull it in that direction, and that's what's going on. Now, how you do it is not particularly hard, but a lot of people get these two mixed up. Do you see how easy that would be to do? It's very easy. Because when you're doing this, you go, oh yeah, that's the same, but then the unit vector is completely different, and this magnitude is completely different. You have to get that right. So the big letter, we'll say this, the big one, the one you are projecting, is the only one you use once. The one, and that should make sense. The one you're projecting upon, onto, that's the one that has your direction to it. That's the one that you should have the unit vector with. That's the one you're projecting upon, which gives you your direction. Does that make sense? That's how I remember it. So when I look at this, the first thing, we're going to draw two pictures, and we're going to do it. It's going to be pretty quick after that. I'm projecting onto A. A should be the one where I get a unit vector, which means A should be this, and A should be this. B is the only thing I have right there. Does that make sense?
Yeah.
If I'm projecting onto B, vice versa. B carries my direction. B is the one I get my unit vector from. B is the one that goes here and here, and that's the way you think about it. If you just have the formulas, it's very easy to get confused. That's why I teach you you need to understand it. Because if you understand that the one you're projecting onto carries your direction, the one you're projecting onto carries your unit vector. The one you're projecting onto is what goes here and here. That's important. So if you feel okay with that one. That's a big deal. It's a really big deal. Now let's practice. So the first thing, how this looks. If I have a vector A and a vector B, what this projection is doing is the original one. It's the original one we talked about. It's taking B and dropping it down to A and seeing what happens. That's what's going on. It's dropping B to A. You guys understand the interpretation of this? I'm going to do the other one right now just so we get it clear in our head. I'm going to try to draw the same picture. This idea is different. Notice the difference. They're not the same. This one says, I want to project A in the B direction onto B. Do you get the idea? This one dropped B onto A. This one climbs A onto B. Well, in order to do that, here's what happens. It goes, oh, okay, let's make it perpendicular. Well, wait, there's nothing there. Yeah, this is a way bigger vector. It's going to be long, even when I project it, it's going to be longer than this. So what's really happening is saying, well, just give it somewhere to project upon. And that purple vector, that's the projection of A onto B. Do you get the idea? It's just, guys, it's honestly all about how much it is component times the direction you're headed, unit vector. This is headed along the A direction. This is headed along the B direction. They're going to be different vectors. They have to be different vectors. You guys see the difference between them? Okay, now it's just a matter of using the formula. It really is just practice. So I'm going to do the first one with you. I want you to do the second one on your own. I'll give you a couple minutes to do that, but let's practice. The main idea, I taught you the main idea. The main idea is, goodness gracious, know what you're projecting onto because it's really easy to mess the formula. We're projecting onto A. A carries the direction. A carries the unit vector. That means A is this piece right here. A should be there. I would write that out. I mean, I don't want to do this in my head. I want to write the formula out with the correct letters. So that should be B dot A. You can't screw that up. I mean, you just dot product the vectors. But this you can. What should this be? Should that be A? Should that be B? What should it be? It should be what you're projecting onto. Here we are projecting onto W, we had W. Here we're projecting onto A. You need A. Figure out that first. The reason why I gave you that, this is the best formula for it, okay, this one. The reason why I gave you that is because this is going to be a scalar, and then you just multiply it by the vector A, and it saves you just a little bit of work. Not a lot, but just a little bit. That's what we're going to do. Show of hands if you feel okay with how that formula works. Why we have the A's where we have the A's. Yes? Let's try it. And the rest of it's going to, it's not too bad. We're going to do a dot product, so we have 2 plus negative 2 plus 3. Check my work too. I'm great at making mistakes on this stuff. Sometimes I do it on purpose, just to see if you're listening. Did you get the same thing I got?
Yes.
This is all going to be a scalar. It could be a number. Now, this one, man, use those. That's why I love this formula, because that magnitude squared is really nice. It says you're going to look at A, and remember the magnitude squared. It's the magnitude without the square root. It's really easy. It's you square all the numbers and you add them. Just don't do the square root. That's why I give you this formula. Okay, A. So 1, 4, 9, done. Because you're squaring them. It's the magnitude squared. You just don't have the square root. Does that make sense to you?
Yes.
What goes here? It is a vector. Scalar vector, that's okay. But this is a vector. Oh my gosh. Looks like 3 what now? 3/14ths? Let's do a little interpretation. I don't want you to leave this hanging. Here's what this says. It says that the part of vector B that is going in the A direction is this vector right here. That's the vector of it. Does that make sense? If you wanted to find how much, the length of it, you'd find the magnitude of that vector right now. That would be the component projection. Or you start over because the formula is really easy and you do the component projection. But that's the interpretation. Show of hands if you're interested in the interpretation of it. Perfect. Can you do it? 10 points. Well, 5 points. You got to do this one too. But 10 points on the test. I mean, that's really it. Sometimes, of course, you're going to have to distribute this. So if your answer is not exactly the same, probably distributed that. But for me, I really don't care. What I do care about is that you can do that one and get it right. Go for it. man, did you do it? Did you get it? Did you get this one?
Yeah.
First thing I'm doing, for real, like first thing I always do, because it's so easy to make mistakes on it, I write up the formula with the correct letters in the correct spots. Do you see how that would be pretty useful to do? Because the formula, you're going to have that formula. Well, I erased it. You're going to have the one that used to be here. Just think back. You're going to have that formula on your note card that you get on your test. You need to know how to plug that in, though. I'm not going to give you V's and W's, or maybe I do, but I give them to you in different ways because I'm a jerk. Ha 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 ha. You have to understand it, okay? So for us, we go, okay, well, what this says is if you understand what direction you're headed in, and you get that that gives you a unit vector, it tells you what letters go where. That's the idea of understanding this. Not just because it's your only other choice because you're switching them, but hopefully understand we're in the B direction. You guys okay with the idea? Please be smart about it. Don't reinvent the wheel, all right? A dot B, B dot A is the same thing. So this is going to still give you that right there. Yeah, you're going to have to do a little bit of work. Hopefully you do the correct work.
Yeah, I
think so. Because we have square, 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 no square root because we're squaring the magnitude. Man, you've learned a lot today. Tell me one thing you're never leaving on a test for me. Please don't do that. Simplify your fractions. So we're gonna change this to our 1/2. In this case, it might be nice to distribute that. I don't care. All right, I really don't. I don't care. Most textbooks will. The only time that they really don't is when you have the whole unit vector idea and then you grow it into another vector. Remember doing that? You multiply the magnitude times the unit vector. So with projections, a lot of times they're gonna. And that's most likely what you're going to see. Have I explained this well enough for you guys to ace this on a test? Good. I hope so. I really hope so. You want to talk about some work? Not that this wasn't work already, but work in the sense of what work means for us in physics, that sort of idea. What work is, how I like to think about work, it's a component of a force, which is a vector. A component of a vector directed along a path in a certain direction. That's called a directed path. Another vector. Have we just figured out how one component of a vector is directed along a different? It's projection. It's a form of projection. The only thing that it is that work is defined kind of specifically. It says that it's multiply, which is what we've been doing. Says that we have, just watch, you're going to see everything that we've just done, okay, if you're still awake out there. It says that we've got some force, right, which is a vector. That's the magnitude of the force. Come on, let's put it together. That's the angle between the force vector and the path vector. Force vector, me, dog, hill. Okay? That's the angle between the force vector and the path vector. This magnitude times this is, if you think back to, I don't have it on the board, but it's on the video. Look back. Okay? Look back at your notes, look back in the video. You're going to notice this. This is component projection. That's exactly what that is. Does that make sense? The only difference between what we've been doing and what we're doing now is we're saying this. This right here is the component of the force along whatever vector I want this thing to move. Okay, my D, my displacement vector. Okay, come on, dyslexia. I don't. Along D. The only difference between what we've done and what we're doing now is that work is defined like this. Work is not a vector. Work is a scalar. It's how much you got done, okay? So what happens is it says, hey, this is the component, this is how much the force is moving, so how much we're applying in this direction, times how far you're moving it, which is the complete displacement, which, okay, come on now. If I have a vector that says I'm going here to here, and I want to figure out how far that is, tell me in terms of vectors what that means. Okay, distance. Tell me in terms of a vector what that means. It's a magnitude. Yeah. Work is a component of a force. Boom. We got it. Component projection. Force along the directed path. Times how much you actually moved it. How much you did. That's what work is defined to be. Does that make sense on what work is right now? Do you see how it relates to what we've been doing? It's kind of cool. Can I just blow your mind with some other stuff here? Can we check this out? Scalar?
Yeah.
Which means it's all commutative, which means that work can be reassociated. Oh, but wait. When I have a magnitude of a vector times a magnitude of another vector and the angle between those two vectors, this thing, look back at your notes, you're going to have to look back at your notes, okay, because I don't have them bored. But there was a definition here. I said, hey, remember that there's an alternate way to do this, and it's really useful, and we're going to talk about it when I do this little proof? Here it is. Force dot displacement equals work. Do you see it? Do you see it? You remember that little definition? If you think back to, you don't have it anymore, but if you think back to here, we had... we had that. Do you remember that? We said, and right before we did that, we had this stuff on this side. And that was this. That's what I'm telling you. So because we have this definition of work, where work is the component of force directed along the path times the amount that you're displacing it, that's what work is. We go, okay, that's fantastic. Wait a minute, that's just a dot product. So what is a dot product? Work. And sometimes it's some work.
Yeah.
That's pretty cool. That's pretty cool. Here's the deal. Just like before, okay? Just like before. If you know the angle between the force and the path you're moving stuff on, which formula are you using for work? This one, because it has an angle right built into it, okay? If you don't know the angle, which one are you doing? That one. So you could do either way. And not if you're okay with the idea. Tell you what, we're going to burn through two examples pretty quick. We're going to do one where we don't know the angle, one where we do know the angle. We're going to get to my dog example, and then we'll talk about the whole unit vector and 3D idea. So. Okay, so first example. Here's what's going on. I got a force vector, so I'm pulling along this vector. I'm pulling along that vector. And what happens is I'm pulling along that vector, but I have this little runner, okay? It's like a track. And this track goes between 2 points. It'd be a pretty lame question if this vector was between those 2 points. It's not, and it's not going to be parallel either. That's the whole point of doing this, okay? It's saying I got this little runner between these 2 points, wherever they are in space, and I've got a force vector that I don't even know what, that doesn't have to be right on top of it. It's pulling. It's going to eventually move from here to here. What we want to figure out is how much work is done when we do that. Because we might be applying a whole lot of force in a wrong direction. It's still going to move it, but we're doing a certain amount of work here, so we're going to figure that out. Do you guys understand the idea on this? Tell me what you have. Tell me what you don't have.
We have points.
You have points. Do you have a force vector?
Yes.
Do you have a displacement vector?
Yes.
Explicitly written out.
No.
Can you find it?
Yes.
Oh, good. Okay, so the first thing here is, okay, which one am I using? Do I know the angle between them?
No.
I could find it, but that's going to suck. So why? Because we have a better formula anyway. We need 2 vectors to find out the work done by moving a point from one spot to another on them. Okay, we got to have that. So the first thing we have is this force vector, and that's great. The next thing we have to do is figure out what our displacement vector is. If you're given 2 points, man, your displacement vector is the position vector of those 2 points. Find that now, okay? My handwriting's just going downhill, sorry. Did you figure it out, the displacement vector? What is it? Tell me an egregious error I just made that none of you are going to make, because I'm telling you right now. Why isn't it a vector? Because all I'm giving you is the terminal points, okay? And I don't want that. So when you're talking vectors, you need a vector. Notice, if I try to do a dot product right now with a point, that doesn't make sense. I got to have vectors. Make it make sense. Egregious. All right. So now I've got a vector force. I got a vector, a displacement. I can do this one of 2 ways, easy way or hard way. I can find the angle between these using all that junk that we just did, and then find the magnitudes and use this formula right there. Or, because I have a force vector, because I have a displacement vector, tell me how you can find work. Do it. Find the work. That's pretty good. Best drawing I've done all day. Only drawing I've done all day, but, whatever. Can you picture the dog?
Yeah. It's a wiener dog.
I don't even have a wiener dog. There's one that comes around, gets in my garage, and walks on my maple top plywood that I'm making cornhole boards out of. Pisses me off. Best I got. Sorry. I'm going to give it away. I don't even know who this is. I'm going to say, hey, you guys want a wiener dog? Cool, I guess. Stupid wiener dog. So yeah, I'm walking someone else's wiener dog now. Yeah, thanks for that. Showed my garage you wiener dog. Did you figure out the work on this? If you know how to do a dot product, yeah, it's not a problem. No problem. So we're going to dot product this 6, 9, negative 3. 12. 12 units of work, whatever those units mean. Did you get the 12?
Yeah.
Awesome. Any comments, questions, anything about that one? Let's do the dog example, okay? So I'm walking up this canal. This canal is inclined of 20 degrees. This canal is a long, I've never heard of a 30-foot canal, but hey, let's just pretend it happens. So I'm moving this dog 30 feet, and I pull up an angle of 30, I'm estimating here, so we're estimating work. I'm pulling up about 30 degrees at about 15 pounds. Because he's actually got like a 70-pound dog, so I'm hoping that I don't have to drag his head. How much work is done? Number one thing I want you to think about is what formula makes sense here. Does it make sense to do a dot product on this example?
No.
A dot product means you're not given angles, all right? And firstly, do you even know what those vectors are? How are you going to do a dot product if you don't even know what the vectors are? I can't do that. You're right. You can't. That's why we get this other one. Look at this form. Look at this formula. This is really a beautiful thing. Do I care? You're not even looking. You should be looking. Do I care what the actual vectors are? No. All I care is the magnitudes. Do I know the magnitude of the force? How much? 15 pounds. Good. Do I know the magnitude of the displacement? How far? Do I know the angle between them? What is it? What about the 20?
It don't matter because it's not predicted.
Does the 20 matter? That always screwed me up in physics. I'm like, what about the 20? It's got to be there for something. It's not. It's not there for anything. It's just telling you, okay, it doesn't matter. That doesn't matter when we're moving it along this vector. It does not matter. What we're talking about here is, okay, I have 15 pounds of work. I'm not talking about gravity right now. We're saying I'm moving this dog. That's enough to move him. So that's what we're talking about. So first thing we okay, work. Did I make it?
No.
Say yes. They can't see it.
Yes.
Yeah. So work. No, because I don't even have vectors, all right? Work goes, yeah, let's talk about the actual magnitude of the force, the actual displacement, and then the cosine of the angle between them. We just talked about, we're going to burn through it pretty fast. The force is 15 pounds, that's the magnitude. The displacement is 30 feet. The angle between them, 30 degrees. Do you know what cosine of 30 degrees is? Yeah, root 3 over 2. That's the exact. So we go, okay. I think that's 450 if I'm doing my math correct. Yeah? I think so. Work is about equal to, so take the 450, multiply it by cosine 30, or multiply it by square root of 3, divide by 2. How much do we get, roughly?
389.7.
Yeah, that's about what I got. That's an awful sign there. Units kind of matter in real life. Units matter here. So 389.7 foot pounds. You put the foot pounds? Moving a pound of we moved 389.7 foot pounds. You ever talked about torque? If you ever worked on any sort of vehicle whatsoever, and you put on like a lug nut, you got to torque them to a foot pound. And we're going to talk about torque in the next section, how we actually get that stuff. Has this made sense so far?
Yes.
Perfect. Any comments, questions whatsoever? Okay. We're going to talk about something that not super used all the time, but it comes up occasionally. And because I talked about the unit circle idea in relation to a unit vector, I want to bring this up. So, last little thing, kind of big thing, but last thing. I want you to get a feel for it, a feel for how the angles work on a vector in 3D. You know how the angles work on 2D because it's really easy. You go, vector, angle, duh. But when we talk about 3D, we have these things that are going everywhere, right, from the origin. I want, the only reason why we're doing this, because I want you to start picturing the angles in relationship to the planes. That's what I want, and it's good for you. So we're going to talk about something called direction cosines. What direction cosines do is tell you how to relate where a vector is going to each of the axes, x, y, and z. That's what they do. How they do it, I'm going to show you. Can you please draw yourself a 3D coordinate system? Do you know how to do that yet? First, draw straight lines. I'm not drunk. I just don't know how to draw good straight lines. So draw yourself a nice, good straight line. Did I ever tell you that story about when I found out this teacher, doesn't matter, was actually drunk in class? It's crazy. And it wasn't me, which is shocking to all of you. Is that a 3D coordinate system?
Did he fall over? No.
I don't want to get into it right now. Got a raise. Promoted. Anyway, which one of these is the x-axis? Yeah, it's that one. That one. That's the x. It's going into the board right now. It's a little awkward because we're trying to represent 3D and 2D, and you can do it, but it's you have to visualize. This one? What is it? And you should be familiar with what the positive and the negative x, y, and z are. Here's what we're going to do. We're going to do is take a random position vector like that one. That I want you to interpret as not being on the plane. It's sitting out here in octant 1. Can you picture that right now? So it's not, it's coming out like this. That's what's happening. Here's what we're going to describe right now. We're going to describe the angles that this vector makes with each of the 3 axes. So here's how to picture it appropriately so that your head doesn't explode, okay? We're going to first talk about the angle this would make with the x-axis. Trust me, you got to listen right now, otherwise it's not going to sink in. Imagine this vector making a cone around the x-axis. Can you picture that right now? Making a cone around the x-axis. It is going to intersect the xz plane and the xy plane. And if you imagine that, it's going to have an equal angle. No matter that angle is going to be the same on those planes. You guys get what I'm talking about. So imagine a cone going around the x-axis. The angle we're talking about is the angle that projection makes from x to the picture on the xy plane, or from x to the picture on the xz plane of that cone. That's the angle. If I imagined it being a cone revolving around the y-axis, that thing's going to intersect the YZ plane. It's going to intersect the XY plane. The angle, that's a second angle, is the representation. So if I make the cone, that angle, that's what I'm talking about. That's going to be the angle with the y-axis. Are you guys getting the idea? Imagine the cone going around the z-axis. It's going to intersect the XZ plane. It's going to intersect the YZ plane. That angle that it makes with the picture of the cone is the angle I'm talking about with the z-axis. You guys get the picture? It's hard to visualize, but you visualize the cone, and it's a lot easier. Okay? Remember, we talked about dogs, right? You ever seen a dog with a little cone on its head? That's what I'm talking about. It's going to intersect here. It's going to intersect here. That angle is what we're finding. And there's 3 of them. There's an angle that does this. This one's the weirdest one. From the x to the vector. We call that alpha. From the y to the vector is beta, and from the z to the vector that way. It's always from the positive axes, okay? It's not from this way. It's from the positive axis. That gets them getting used to, okay? The angle measurement from the z is dropping. It's not climbing, because that'd be from the negative. It's from the positive. Oh, what do we call that one? I think we call it gamma. I'm horrible at gammas, by the way. Are you horrible at gammas? That's the best I got. Actually, it's not bad for a gamma. Because I'm not Greek. Did you know that? No, you can tell. But whatever. Alpha, beta, and gamma are called the direction angles of our vector. You ready for it? You ready? Ready for the first question? Hey, everybody in class right now, tell me the direction vector of the x-axis. Tell me what it is. The direction vector. The unit vector that represents the x-axis. I. Thank you. Oh, I see now. I get it. Let's try it again. Maybe you can get this one. Everybody in class, right now, tell me the direction vector of the y-axis.
J.
Oh, geniuses. That's right, all of you. The direction vector of the z-axis, what's that?
K.
Perfect. If I want to find out the angle that a vector makes with another vector, all I have to do with that cosine is called the direction cosine. All I have to do for that angle is dot product the vector and the vector that I'm given and the vector that I want to find the angle between. If I want to find the angle between the vector and the x-axis, you just told me right now that I kind of missed. Still not drunk. Don't worry about it. I just missed my line, okay? You just told me right now that I is that direction. Does that make sense? Are you sure you're with me?
Yes.
All right. You guys okay with it? Do you see where it's coming from? That's where I really want to know. Do you see where it's coming from? This says, I want to find the angle between V and I. What's I? Oh, the x-axis. That says that this is now going to give us, I'm sorry for erasing that, but that's going to give us alpha. The angle between V and I is what alpha is defined to be. Do you guys get it? Now, let's make it even easier. And it's going to make a lot more sense. We make a lot of sense when we do this. Let's make it even easier now. Let's actually dot product V and I. I'm going to do it over here, but I'm going to erase it, okay? So let's do that. Here's V. Yes, no? You sure? Just random vector, right? You need to know this. What's I? Come on, quickly. Someone said it earlier, but everyone say it. What's I? Let's dot product them. You all know how to do it. You multiply and you add. What am I going to get out of that dot product? Just V1. So this is simply V1. Not a vector, just a number, because it's dot product, scalar. Just V1. Show of hands understand that concept. Now, how about this one? How about the magnitude of I? We need to know that one. What's that? 1. Magnitude of V, I don't know. That's the only thing we really have to work on. Well, here's what we just learned about the cosine alpha, the angle that the vector makes with the x-axis. Cosine alpha equals V1 over the magnitude of V. Please stop what you're doing right now. Just listen for like 5 seconds, okay? This should make absolute sense just by the logic of the cone and what a right triangle does. Think about it. If I had this cone and it moves it right here, so this vector's coming up like this. The magnitude of the vector, that's the length here, drop a perpendicular, cosine of the angle takes hypotenuse over adjacent. Oh, sorry, I had that backwards. Adjacent over hypotenuse. Takes adjacent over hypotenuse. If you solve it for that cosine, that's what this is. That's the adjacent. Look at the adjacent. The adjacent is the x component. You guys see it? That's the x component of the vector. Divided by the magnitude, that's literally what a right triangle does. This is adjacent over hypotenuse. Done. Did you guys see it? A lot of proof for it, but it's just adjacent. And so what that means for us, for cosine beta, I'm not going to do the whole proof again because it's really easy. If I wanted to find the angle between the y-axis, check it out. This beta, I would just pretend it's on the plane. It would be adjacent. That would be the y component over hypotenuse, the length of the vector magnitude. And likewise for gamma. Y'all okay on the idea behind this, for real? We're going to do maybe just like 1 or 2 examples. We'll call it good. There's one other thing that I need to show you, and then that's it. First one's that. I'm going to prove it right here with just some talking through. You know what? It's too easy to. I'll just prove it right here. I passed that you guys as well, right? Second time? Okay, good. Hey, think about it. If cosine alpha is this, and cosine beta is this, and cosine gamma is this, and you square them all, look what happens. Look what happens. I get magnitude squared, magnitude squared, magnitude squared as a common denominator. I get V1, V2, V3 all squared respectively, which says, okay, this is... that, but we learned something earlier. Come on, everybody, you got this. What is that? That's the magnitude squared. That's 1. That proves it right there. So that's a really neat relationship that we can use on these things. If you ever have to find the unit vector, there's a quick way to do it. Here's how you find the unit vector. It's just like finding the unit vector from the unit circle idea. It's just a little extension. It doesn't have any signs because we didn't use sign up here to talk about the relationship between the axis and the vector. But that's the equivalent. That's the way you can find unit. If you know the direction angles, that's the way you can find the unit vector. Does it make sense for you? Do you guys want to do an example, or do you feel okay with it? You want to do one?
Example, yeah.
Yeah.
Okay. Can you use this to figure out what alpha, beta, and gamma is going to be? First thing I want you to do, just find the magnitude, because you're going to use it in all three of those cases. So number one thing I'm doing is magnitude of vector v. Not magnitude squared, gotta have magnitude. So I know I'm going to be working with square root of 35 a whole lot. Okay, we're going to burn. Okay, we're going to go really, really fast. Cosine alpha. You tell me the component that I need for cosine alpha. Is it x? Is it y? Is it z? It's really convenient, right? Because alpha has to do with the x-axis. It's the x component. So tell me specifically what I have. Over? Could you find alpha from this? How would you find alpha from that? Notice something? That's going to be more than 90 degrees. More than pi. Why? Well, cosine's negative. That happened in the second. We can't go third or fourth, right? Because that'd be too far around. We'd get there shorter another way. Also, notice this vector. It says, hey, on the x-axis you're going negative. You're going this way. You're going more than 90 degrees. That should make sense. When you get that negative number, it's more than 90 because you've gone past the y-axis. You're now in negative x land. Does that make sense? Cosine beta, man, you can do it. It's 3 over square root of 35. And then cosine gamma, 5 over square root of 35. You can do the cosine inverse and get nice approximations of those things. Have I made this stuff make sense for you? Yeah, question?
I'm just a little unclear about the negative cosine alpha, how it correlates to that. You said it goes over the 90
sure.
degree.
Imagine if you, on your vector, your first step is going -1, correct?
Yes.
-1. So -1 is this way.
Yes.
In order to make that work with my x-axis, that
Gotta
angle,
go through the y.
that's going past the y into negative x land. That's more than 90 degrees. That's what I'm talking about here. The other two are going to be less than 90 because I'm in positive y land, I'm this way, and positive z land, I'm this way, I'm not past it. Does that make sense?
Yes.
Pretty cool. Anyway, that's about it.